All right, so now we're going to jump into how batteries work. So redox reactions result from electrons being transferred from one chemical compound to another. So if you were to look at this equation right here, copper 2 plus aqueous plus zinc solid produces zinc 2 plus aqueous plus copper solid. Okay, this is a redox reaction. Your copper goes from a +2 oxidation number to a 0 oxidation number, so it's reduced. Whereas your zinc goes from a 0 oxidation number to a +2 oxidation number, so it's oxidized. Okay, what if we were to take our aqueous copper solution and put it in a container here, and then take our solid zinc and put it in another container here? They can't come in contact with each other to transfer their electrons. But what if there was a way for the electrons to travel, right? What if we put a wire in the container? So that's what they're doing right here, so that each end of the wire was in contact with each substance. So that wire would be your conductor, right? It's a means for the electrons to move. The zinc would want to lose its electrons, so they would travel along the wire on their way to the copper, okay? That can't happen quite yet though, because when it loses the electrons, the zinc ions would result, but they can't exist by themselves, okay? But they can exist in water. So right here, if we fill the container with water and aqueous, this will allow the zinc ions to form, the zinc 2 plus, as the electrons are transferred to the copper container along the wire, right? Solid copper would begin to form, but it will happen more easily if there's already a piece of solid copper in the container, okay? So now the reaction can proceed. So you see, we just need to make a way for the electrons to move from the solid zinc to the copper solution, right? That's the whole purpose of the wire. It's the conductor to transfer the electrons. As the electrons leave, the solid zinc atoms will become zinc +2 ions, but they need to do that under aqueous conditions like I just explained, right? Okay, so this reaction can occur even if the actual reactants do not come in contact with each other, as long as there is a way for the electrons to move. The reaction can begin and the products will start to form, okay? Eventually, the solid zinc strip will begin to slowly disappear, right? The zinc atoms becoming ions and dissolving into the solution. Now, at a certain point, the reaction will stop. That's because once some of the electrons leave the solid zinc, it becomes zinc +2 ions, and they dissolve into solution, and they make the entire solution in the container have a positive charge, okay? The more and more positive that solution becomes, the less and less likely it is for electrons wanting to leave it. That's because that positive charges will attract the electrons to itself, right? And simultaneously, the electrons that did make it to the copper solution will begin to make that solution more and more negative. That will repel any electrons that are moving along the wire on their way over. After a few electrons move along the wire, then the reaction would stop because the electrons would no longer want to move along the wire. But to help this, to prevent this from happening, that's why a salt bridge right here is added to the system. So what is a salt bridge? So a salt bridge contains a salt, which is just an aqueous ionic compound. Remember, when ionic compounds are aqueous, their ions break apart and they can move independently around, right? So let's say we had sodium chloride, NaCl, in water. The positive sodium ions would break apart, and the negative chlorine ions would break apart. They'd separate and they move around the solution. So with a salt bridge, when the zinc container begins to become positively charged as the electrons leave it, right? As the electrons leave this, it becomes positively charged. The negative ions within the salt bridge move toward that solution right here. They'd move towards the solution. that would cancel out the positive charge so that more electrons can continue to move along the wire. And similarly, as the copper container becomes more negative, as the electrons enter this will become more negative. The positive ions within the salt bridge, right here, the positive will start to move over here so that it'll cancel out the negative charge. So more electrons can enter. This is how a battery works. Okay, salt bridges are needed within a battery because they contain aqueous ionic compounds that will help to balance out the charges that would otherwise result and form in the two containers. Okay, so, all right, so in a battery, electrons leave solid zinc. We know this because the oxidation number of zinc shows us this. The electrons travel to the copper, 2+ solution, and we know this because copper, the oxidation number changes, right? Electrons flow from the zinc to the copper. When electrons travel along the wire, we have electricity, okay? So the reason why it makes electricity is because the electrons move along the wire, and this is how electric devices run. We add a specific device called a voltmeter, right here to our wire, and it measures the potential difference between the 2 points. So when you think of a D-cell battery, okay, it has 2 ends, right? It has 2 ends. If we connect a voltmeter to the 2 ends of a battery, it will read approximately 1.5 volts. That tells us the battery's voltage, okay? The setup we had of zinc and copper solution is a simplified design of a battery. You guys know that a lot of batteries, most batteries we use look like this, right here in this picture. So you're probably familiar with various ones. We have AAA, AA, C, D, 9 volt. All these batteries have 2 ends. They have a positive and a negative end. Most are found this way. And then your 9 volt you've got right here. So I want you to consider a previous battery setup, okay? Where's the positive and the negative side if we're looking at the setup here? Electrons are flowing away from the zinc, so the container of zinc is thought of as the negative charge, okay? Negatives come out of it. Because electrons travel toward the copper solution, we can think of it as positive because it draws negative to itself. So right here, so we can now give the battery some terms. The negative side of a battery is the anode, okay? It's the source of negative ions called anions. And the positive side of the battery is called the cathode. And it's the source of positive ions called cations, all right? This type of setup is called a galvanic cell, okay? Within the cell, we have metal strips we call electrodes. Copper electrode and zinc electrodes. Okay, so we've got electrodes right here. They form the, I think I said from, they form the electric contact between the wire and the contents within the container, right? So you have your electrodes connected to your wire, and then they're in the solutions, right? So all batteries eventually run out, because as a battery is producing electricity, electrons are moving from one reactant in the battery's chemical reaction to the other one. And at some point, the reactants are all used up. There's no more electrons flowing and the battery dies. Okay. Some batteries, like the ones you have in your phone, your laptop, are rechargeable. Okay. How's that work? When a battery is dead, it has no more reactants. A battery charger creates an electric force to reverse the battery's chemical reaction, all right? And what would that do? It would create more reactants again. So by plugging in your device into an electrical outlet, that energy can force the product of the original reaction to react with each other and reform reactants, okay? This should make sense based on what you guys have learned so far about reactions. All right, so I want to work through an example for you guys. So this one says, a galvanic cell runs on the following reaction, and I have it right here for you. 3 Mg solid plus 2 Al3 plus aqueous goes to 3 Mg 2 plus aqueous plus 2 Al solid. Draw a diagram for this galvanic cell, labeling the electron flow, the anode, cathode, and the positive and negative sides of the galvanic cell. All right, so what I started with is just my basic diagram before I'm gonna add to this. And then what I'm gonna do is find out the oxidation number changes. All right, so Mg goes from an oxidation number of 0, and it changes to an oxidation number of 2. So what do we know about this? Leo. Lose electrons oxidized. Oops, there's an ant there. Okay. And then for our, it goes from an oxidation number right here of +3 to 0. So this is our GER. Gain electrons reduced. So it's reduced. Okay, so this tells me what I need to know for my galvanic cell for my drawing. So this is going to be my Mg electrode. That's solid. And then I'm going to get, when they break apart, I'm going to get these ions right here. And electrons are going to flow out of this diagram, which means that my negative ions are going to flow in from my salt bridge to counteract, and this is going to be my negative anode. Okay, this over here is my other electrode. I'm going to have 3+ ions in my solution. My electrons are going to be coming in, and my salt bridge is going to have my positive charges coming in, right, to balance out. And this is going to be my cathode. All right, and that's how you would work this problem. All right, we're going to finish up this module. Experiment 16.2, you basically build a galvanic cell with a lemon. I'm going to see if I can find an example of that online. Hopefully I can. But we're moving into the section on real batteries. So you guys probably know, or maybe you don't, but as batteries become smaller, their designs are more complicated, okay? So it's important to have a general understanding of how they work. And right here, they're going to start talking about car batteries, which are also lead acid batteries. So it utilizes this reaction right here. And when you look at what is becoming oxidized and what is becoming reduced, you might notice right here that you have Pb, lead, and you have lead here, and one starts at +4 and one starts at 0. And then over here, you have it going to +2, right? So you actually have one lead atom that's being oxidized and the other is actually being reduced. They just end up making the same product, okay? Sulfuric acid is the acid that's in car batteries, and that's why you have to be really careful with them. Another thing to note is they are rechargeable, right? Otherwise your car battery would die sooner than it actually does. But there's the alternator, which helps force the reaction to run in reverse, which we talked about earlier, why that would help it be rechargeable. And also, you can see that this reservoir right here is filled with your aqueous sulfuric acid. So this is, it has a salt bridge, it's in an aqueous solution. So this is what we've been talking about, okay? Now, when we talk about these kind of batteries, right, which you're more familiar with, there are no aqueous solutions in them, right? So that's why they're often referred to or called dry cell batteries. So that's just a good thing to note. All right, guys, so that's all I have in covering this last module. Stay tuned for my final test. I'll get that uploaded. If you have any questions, please let me know. And once you take this test, congratulations, you finished high school chemistry.